this episode, we're going to make the everyday web feel less like a black box by unpacking what actually happens when your browser talks to a website. Most people experience the web as clicking links and filling out forms. But underneath that simple experience is a very structured conversation with rules, patterns, and lots of security implications. When you hear about attacks like session hijacking, cross-site request forgery, or insecure cookies, those stories are really about the mechanics we're covering today. The good news is that you do not need to be a programmer to understand what HTTP is doing, because it's mainly about requests and responses moving back and forth in predictable ways. We'll walk through methods, headers, cookies, and sessions in a way that gives you a clear mental model for how web applications keep track of you, how they make decisions, and how mistakes turn into vulnerabilities. A strong starting point is to remember that Hypertext Transfer Protocol, HTTP, is a set of rules for a client, usually a browser, to ask for something and for a server to answer. The browser sends a request that includes a method, a target location, and a bunch of supporting details, and then the server returns a response that includes a status, some supporting details, and usually content. The content might be a web page, an image, a piece of data, or a message that says nothing is available. Even though modern websites feel dynamic, this request-response pattern is still the backbone, and almost everything else is built on top of it. That's important because security is often about controlling what requests are allowed and making sure the server responds safely. When you understand what the browser is allowed to ask for and what the server is supposed to do with that request, you can reason about how attackers try to bend those rules. The method is one of the first clues about what the client intends to do, and it's often simplified as a verb for web actions. A very common method is GET, which is used to request a resource, like loading a page or fetching an image or retrieving data. Another common method is POST, which is often used to send data to the server, like submitting a login form or placing an order. There are other methods too, such as PUT and DELETE, which can be used for updating or removing resources in certain designs, but beginners should focus on the core idea that methods communicate intent. The key misconception to avoid is thinking that a method automatically enforces safety, because it does not. A server can be misconfigured to accept dangerous actions through the wrong method, and an attacker can choose whichever method triggers the server's weakest path. To make methods feel concrete, imagine the difference between asking to view a product page and asking to change a shipping address. Viewing a page is typically safe because it should not change anything, and that aligns with the usual expectation for GET. Changing a shipping address is a state-changing action because it modifies data, and that aligns more with POST or similar methods. The security issue appears when a state-changing action can be triggered in a way that looks like a harmless view, because that makes it easier to trick a user or bypass controls. That's one reason you will hear security people talk about safe methods and unsafe methods, where safe means intended not to change state. It's not a magical guarantee, it's a design expectation, and a lot of web security relies on designers following those expectations consistently. When they don't, you get confusing behaviors that attackers can exploit. Next, let's talk about headers, because headers are the metadata that gives the request and response their context. A header is a named piece of information, like the type of content being sent, the language preferences of the client, or the identity of the host being requested. In a request, headers can tell the server what kind of browser is connecting, what formats the browser can accept, and what prior state it might already have cached. In a response, headers can tell the browser what kind of content it is receiving, how long it can cache it, and whether certain protections should apply. Headers matter because they are frequently used as decision points, and decision points become targets. If a server trusts a header too much, an attacker may be able to manipulate that header to change behavior, bypass restrictions, or confuse logging and monitoring. One of the most important response headers for security is content type, because it tells the browser how to interpret the response body. If the server says the content is HTML, the browser will render it as a page. And if the server says it is a simple data format, the browser might treat it differently. Mistakes in how content type is set can contribute to issues where the browser executes something that was meant to be treated as plain text. Another important area is caching-related headers, because caching can accidentally store sensitive information in places it should not be stored. Security headers can also instruct the browser to behave more defensively, but those protections depend on correct configuration and consistent behavior. Even if you never memorize every header name, you should remember that headers are powerful hints that shape how the browser and server behave, and power is always something attackers try to misuse. Cookies are the next major concept, and they often confuse beginners because they sound like a small browser feature when they are actually a core mechanism for state. A cookie is a small piece of data that the server asks the browser to store and send back with future requests. The browser doesn't decide on its own to create a cookie for a site. It follows the server's instructions and stores it under rules about which site it belongs to and when it should be sent. Cookies are used for many things, like remembering preferences, keeping you signed in, and tracking the contents of a shopping cart. From a security viewpoint, cookies become critical because they can carry identifiers that represent who you are in the eyes of the server. If an attacker can steal or manipulate those identifiers, they may be able to impersonate you without ever knowing your password. To understand why cookies exist at all, you need the idea that HTTP is stateless by default. Stateless means each request is independent, and the server doesn't automatically remember what happened in the last request. That's great for simplicity and scale, but it's not great for building a website that needs to remember that you logged in or that you added items to a cart. Cookies are one of the main ways the server creates continuity across separate requests. Instead of the server remembering everything, it gives the browser a token, and the browser presents that token on future requests. This turns a series of isolated requests into something that feels like an ongoing conversation. That ongoing conversation is what we usually call a session, and sessions are where many high-impact web attacks live. A session is essentially a way for the server to recognize that multiple requests are part of the same user interaction over time. The simplest mental model is that after you authenticate, the server creates an entry on its side that says this user has an active session, and it gives your browser an identifier that points to that entry. The browser then includes that identifier in each request, often via a cookie, so the server can look it up and apply the right permissions. Sessions are powerful because they represent your logged-in identity, which means a session identifier is often more valuable than the password itself. If an attacker gets the session identifier, they may be able to step into your logged-in state without triggering another login. That's why session management is such a high priority in web security, and why settings on cookies and timeouts on sessions matter so much. Now let's connect this to typical security failures that show up again and again. One common failure is storing the session identifier in a way that makes it easy to steal, such as exposing it in places where it can be logged, cached, or leaked to third parties. Another failure is allowing the session identifier to be reused too broadly, such as not tying it to important context like changes in authentication state. You also see problems when a session lasts too long, because the longer it stays valid, the longer an attacker has to benefit from stealing it. Sometimes the issue is that the application does not regenerate session identifiers at key moments, like after login, which can open the door to session fixation, where an attacker tries to force a victim to use a session identifier the attacker already knows. The details can get technical, but the big idea is simple. Sessions are the web's way of remembering who you are, and anything that weakens that memory can be exploited. Cookie attributes are a major part of how defenders reduce those risks, because they tell the browser how carefully to handle the cookie. Secure is an instruction that the cookie should only be sent over encrypted connections, which helps reduce theft on insecure network paths. HTTP only is an instruction that the cookie should not be accessible to typical client-side scripting, which helps reduce theft through script-based attacks. SameSite is an instruction that affects whether the browser will send the cookie in cross-site situations, and this is central to reducing cross-site request forgery, because those attacks rely on a browser automatically including cookies in requests triggered by another site. Beginners sometimes think these settings are minor, but they are actually part of the browser's guardrails. They do not solve everything, but they significantly reduce common attack paths when configured correctly. Cross-site request forgery, often shortened to CS or F, is a great example of how web mechanics become a security problem even without malware. The basic trick is that your browser is willing to send cookies automatically when making a request to a site, and attackers try to cause your browser to make a request you did not intend. If you are logged into a bank, for example, and you visit a malicious site, that malicious site may try to trigger a request to the bank that performs an action, like changing an email address. The bank receives a request that includes your session cookie, so it looks like you, even though you did not initiate it intentionally. Defenses involve requiring additional proof that the action was intended, such as unique tokens tied to the user's session and the specific form interaction. The key learning is that browsers do helpful automation, and attackers try to turn helpful automation into unauthorized action. Another common web security story is session hijacking, where the attacker gets the session identifier and uses it to impersonate the victim. This can happen through many routes, like intercepting traffic on an insecure connection, stealing cookies through certain client-side vulnerabilities, or obtaining session identifiers from logs or exposed storage. Once the attacker has the identifier, they don't need to crack a password or brute force anything, because the server will treat them as already authenticated. This is why encrypted connections are a baseline expectation for modern web usage and why cookies that represent sessions must be handled with care. It's also why logout and session invalidation matter, because a session that stays active after a user thinks they are done increases risk. Again, the mechanics are simple, but the consequences are huge. It also helps to understand that the server communicates success or failure through response status codes, which are like short summaries of how the request went. A successful request often returns a 200-level code, while redirects are typically 300-level, and errors show up in 400 and 500 levels. You don't need to memorize every code, but you should understand that these codes are signals for both users and attackers. Attackers probe applications and watch for differences in status codes, response sizes, and timing to learn how the system behaves. Defenders use these signals to detect scanning, brute force attempts, and abuse patterns. Even a beginner can grasp that consistent, predictable responses are safer because inconsistency can leak information about what exists on the server and how it is protected. This ties back to the broader idea that web security is as much about controlling information exposure as it is about blocking actions. To bring all of this together, here's the core concept you want to carry forward. HTTP is a request-response system, and the richness of the modern web comes from layering state and context on top of that stateless foundation. Methods communicate intent, but do not guarantee safety. Headers shape how clients and servers interpret data and enforce policies. Cookies are the browser's way of storing small pieces of server-provided state, and sessions are how servers remember your authenticated identity across many requests. Most web attacks are not mysterious once you know these mechanics, because they usually target one of three things: confusing intent, stealing identity tokens, or tricking the browser into performing actions with stored credentials. When you read about new web vulnerabilities, you can often classify them into one of these buckets, even if the details sound complex. That classification is what makes security learning feel manageable instead of overwhelming. As a final takeaway, aim to think of web security as protecting conversations, not just protecting pages. A page view is not just a picture you see. It's the result of a request with a method, headers, and sometimes cookies, and it produces a response with status and rules that guide the browser. When those conversations are designed carefully, the server can confidently know who is making the request and what they are allowed to do, and the browser can safely interpret what it receives. When those conversations are designed carelessly, attackers can spoof intent, steal session identifiers, or exploit browser automation to take actions the user never meant to take. If you keep this mental model clear, you will be able to understand why modern defenses focus so much on cookie settings, session lifetimes, and consistent request validation. That clarity makes it much easier to learn the security topics that build on top of these mechanics later in the course.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.